Welcome to the webinar. Today I want to speak about the basics of power transformers as used in switch mode power supplies. This is a continuation from the basics of power inductors we did recently. I want to pick up where I left off last time when we were talking about flyback transformers, which are a type of crossover device. And then I want to get into how transformers work, a little bit about the equivalent circuit, then talk about the main parasitics, leakage and capacitance. We want to talk about core loss and winding losses, which are the major losses in transformers, and then about how transformers are used in different types of topologies. The forward converter, which is unipolar, and then into push-pull, which is bipolar, the half and full bridge, and Llc. Then I want to touch on safety agency requirements. These are photographs of Michael Faraday's induction ring from 1831. You can actually still see it at the Royal Institution in London. He's the one that got us started by discovering mutual inductance. The year 1831 is also the year James Clerk Maxwell was born in Scotland. Last time we talked about the flyback transformer. We said it was an inductor because by definition it stores energy, but because of the topology where it's using two separate inductors that share the same core, there's mutual flux. Because of that, it has the transformer property of turns ratio, and therefore the voltages and currents are proportional to each other, but unlike a transformer, they act independently. Also, a separate coil for input and a separate coil for output has the property of galvanic isolation. So to recap, we use an inductor to impede the flow of current, and we use it to store and release energy from its magnetic field. A transformer, on the other hand, transfers energy instantaneously through its magnetic field. It does not store energy, and it's used to change voltage and current and to provide galvanic isolation. It's interesting to note that it wasn't until 1885, more than 50 years after Michael Faraday's induction ring, that the term transformer was first used. These Hungarians, Bladley, Derry, and Zipernowski, were the first to use the word transformer when they filed a patent for this device, which you can see in the lower right. By the way, you can also see this at the museum in Munich, Germany today. I want to point out how extensively magnetics are used in switch mode power supplies. You can see in this example of an open frame power supply how many different magnetics are used. In order to be a good power supply designer, it's important to understand how they work because they play a critical role and have a big influence on performance. One of the main features a transformer brings is galvanic isolation. That's isolation with no direct electrical connection between the input and the output. It's a safety requirement, and you can see in this schematic where they have nicely delineated where the isolation barrier is. The transformer is a component that transfers the power across the barrier through the magnetic field. And on this circuit board, it's clearly shown where the safety barrier isolation is. There's a minimum distance for creepage and clearance, which we'll talk about later in the presentation. The transformer spans this gap, but it too must maintain the same distances inside it. Conceptually, a transformer works quite simply. You have a high permeability magnetic core that links two windings together. We typically call one winding the primary, which is connected to the source, and the other the secondary winding, which is connected to the load. When the current flows through the windings, a magnetic field is created. The field is magnified by the core's permeability, and it links the two windings together. The flux, voltage, and turns are linked by Faraday's law, making voltage proportional to the turns. With this, we can boost or reduce voltage simply by changing the turns of the secondary. Because energy cannot be created or destroyed, in the ideal case, power coming out of the transformer must be the same as going in. Therefore, the currents in each winding change inversely with the voltage. This flexibility allows us to design a low voltage, high current welding transformer or a high voltage ignition coil using the same principles. The little dots which you see on schematics are called polarity dots, and they indicate the polarity of the winding. The dot end of all windings have the same voltage polarity. This helps you to connect windings in series or parallel if needed. When you connect the primary to an alternating source, several things happen. There's some current flowing in the primary, and this current is limited by the impedance of the windings, which is based on the inductance, which in turn is based on the permeability of the core material and the number of turns in the magnetic path length. This current creates magnetic flux within the core. We call this magnetizing current. The secondary is open, not connected. There's no power being delivered, so whatever power is being consumed is only to magnetize the core. Since it's not being delivered to the load, it's a loss. In a transformer, you want to have high inductance on the primary to have low exciting current in proportion to the load. At this stage, the alternating flux, by Faraday's law, you're going to have an induced voltage on the secondary winding. This voltage will be proportional turns ratio between the two windings. Now when a load is connected, it starts to draw current. That current creates its own flux. The impedance of the load is reflected back to the primary, which will lower its impedance to the source, causing more current to flow in the primary. The circuits immediately balance according to the turns ratio. The interesting thing about a transformer is this. When we design a transformer, we determine a maximum operating flux based on volt-seconds, not current. We want the magnetizing current to be small, but current creates flux, and by loading the transformer, we increase this flux, often more than tenfold. This flux could easily saturate the core if it were not for the fact that the flux created by the primary and the secondary windings are opposite, and they cancel each other, leaving us with the net flux of the magnetizing current. That's the blue, red, and orange arrows are trying to illustrate. It's one of the great things about transformers. No matter what the load, the transformer will not saturate. You just have other problems. Another thing about polarity dots, if the current is flowing in a polarity dot in the primary, then it's going to be flowing out the polarity dot in the secondary. You can also see a transformer can work both ways. There's no particular reason why you can't flip the source and load around, and the same principles apply. In this case, the transformer would be step up the voltage. The transfer of energy is not perfect. There are many parasitic elements we have to deal with. Most obvious is DC resistance of the windings themselves. There's going to be some leakage inductance because the fluxes generated by the primary and secondary do not link completely with each other. Leakage represents a small amount of stored energy. In addition, there will be some AC winding losses depending on winding layering and the frequency of operation of each of these coils. There'll be some intra-winding capacitance, that's between the turns, because you have voltage gradients and differentials. This will ultimately ring with the inductance at a frequency we call self-resonance. There's also going to be some intra-winding capacitance, that's between the windings, and that will be able to pass common mode noise. One measure of leakage inductance and its effect on a transformer is called coupling factor, with a small letter K. It's a number between 0 and 1, where 1 is perfect coupling. Good transformers couple very well. If you had only 1% of leakage inductance, the coupling would be 0.995. So transformers are very efficient, especially when you have a good high permeability core. Here is a basic lump element equivalent circuit of a transformer. We're trying to show the basic features that would be involved in an equivalent circuit without getting into any great detail about each element. First, we split out the windings and apply the turns ratio to the perfect transformer. The nomenclature for turns is capital N subscript P or S for the individual windings. The ratio is written with a small letter n, such as n:1 or 1:n. There's no standard as to which winding is a reference, but typically you'll find the winding with the fewest turns is the reference. In a step-down transformer, the secondary would be 1. In a step-up, the primary would be 1. Just be careful when you're reading the literature. We have the magnetizing inductance, which we showed you earlier. So you can see that it is in parallel with the output, so the current flowing through it is not going to deliver any power to the load. The same thing with the core loss, where we use RC to represent the losses from the core itself. Again, any current that flows through this path is not contributing to the output, so it's a loss element that we're trying to minimize. We have the leakage inductances as I showed you in the previous slide. They're in series, and as inductors they do store some energy, which becomes a source of voltage spikes. The winding resistances RP and RS include both the AC and DC resistances together. You can see these series elements create a voltage divider, which means that the voltage across the perfect winding is less than the input voltage. If you had a 100-volt source, the voltage at the perfect winding might only be 97 volts. Then you transfer it by the turns ratio and lose some more across the secondary side series elements. We know that the voltage drop across the resistance is proportional to current, which means that this voltage divider is dynamic. The term regulation is used to describe the change in secondary voltage between no load and full load. There's also the Intra-Winding Capacitance. This is the capacitance of the winding turns. It's in parallel element, so any current going through it is not going to make its way to the load, making it a loss element. The interwinding capacitance provides a bypass for high frequency currents. Sometimes you'll see equivalent circuits with a capacitor on top and bottom, which makes it easy to visualize common mode signals passing through your transformer. This is something that has to be considered more and more as the switching speeds increase with silicon carbide and gallium nitride. It's interesting to note that all the elements circled in red are frequency dependent, so they're impedances, not fixed values. The only thing that is fixed is the DCR, but there is an AC component to this winding resistance, and that would be frequency dependent. AC winding resistances and core losses are challenging to model, and several interesting methods have been proposed over the years, but we can't cover them here. Sometimes you'll see all the secondary side elements transferred to the primary side, and this can be done by the square of the turns ratio because they're all impedances. Even though the amount of leakage inductance is small, it's one of the main parasitics that we have to deal with. The leakage inductance is based on the physical construction of the transformer. If you look at the formula for inductance of a long solenoid, you can see that mu naught times turns squared times the area of the coil divided by the length gives inductance. When you calculate leakage inductance, it's exactly the same formula, with the only difference being the area is the area between the windings and partially into the windings. This is illustrated here where H INS is the thickness of the insulation. The permeability of copper is practically the same as air and the insulation, so we take 1/3 of each winding height. Summing these and multiplying by the mean turn length of the insulation gives us the area. From this, we get an approximate calculation. Note that there's no core involved with this. What are the effects of leakage inductance? There are two effects, one with the current and one with the voltage. It delays the transfer of power. For current, the inductance limits the rate of rise of current, so instead of a perfectly perpendicular rise, it has a small slope that delays the current rise. While this is happening, there are losses during the transitions before the fully on state. On the voltage side, when the switch turns off, the energy in the leakage inductance has to come back into the circuit, and it usually manifests itself as a spike across your switch or diode. If it's too big, it could destroy your semiconductor, so you may need to put a snubber across it. Doing so usually results in dissipating the energy as heat, wasted energy again. There are only 3 ways to reduce the leakage inductance. You can see them by looking at the formula for inductance. The best way is to reduce the number of turns because that's a squared element with the most impact. Unfortunately, that's often the one thing you can't do, so you're left with the other 2, which are to reduce the area, the space between the windings, or increase the winding length. The windings that carry the highest power have the strongest fields, so they should be next to each other. Putting an auxiliary winding between a primary and secondary is not always the best idea. Sometimes you must because you need a shield. You want to minimize the thickness of insulation between the windings, but safety requirements dictate minimums. Solid shields, as already mentioned, should be avoided. If you could use bifiler windings. These are not used in power transformers, but they are commonly used in signal transformers. Increasing the winding length is one of the easiest things you can do. You want long windings with few layers, and the way to do that is to split it by interleaving one of the windings. One split in a power transformer is the most effective because each split requires extra insulation. This effectively doubles the winding length. It's important to use the same winding length on all of the windings, no partial layers. They need to be spread out. Often parallel strands are used to fill up space. If you're using a C core or a U core, you can use two-coil construction where you put half your primary and secondary in one coil and the other half primary and secondary on the other coil, joining them in series. This effectively is the same thing as interleaving. You're increasing the winding length. Anything you do to reduce the leakage inductance in all probability is going to increase the winding-to-winding capacitance. Every time you energize a transformer, you're going to have voltage gradients all over the place, and where you have voltage gradients, you're going to have capacitance. It's between the turns, between the layers, between the windings, between the terminals, between the core and the windings, and between the core and the terminals. It's going to be everywhere, and this is all stored energy that it does not get used in the circuit. What are the effects of winding capacitance? For voltage, it slows the rise time of the leading voltage edge because with capacitors it takes time to change voltage, but current can change instantaneously. That instantaneous current shows up as current spikes. If you go back to the equivalent circuit we looked at earlier, the first element was a capacitor. When the switch turns on, any stray capacitance gets charged first, resulting in a voltage spike on the current waveform instead of a nice clean ramp starting from zero, because there's nothing to stop the current. Of course, in any type of current mode controlled converter, if this spike were to exceed the peak current limit, it would shut down. Not the behavior you want. The spikes also create noise that you have to deal with as well. Capacitance is going to limit the operating frequency of your transformer because it resonates with the inductances, and you have a practical limit to the frequency response of any transformer. Again, you can very roughly calculate the winding-to-winding capacitance based on the principle that we consider the windings to be solid sheets. Just imagine the facing layers as place of your capacitor. There's a distance between them filled with a dielectric. Using the mean turn length and the winding width to determine the plate area, the distance between them, and the permittivity of free space, and the permittivity of dielectric yields the capacitance. To reduce winding self-capacitance, changing the permittivity of your insulation is one option, but most insulation materials are pretty similar, but it's still an option. We want to reduce the area if we can by reducing the winding length. We wouldn't want to interleave it. If we can make the part smaller, it would reduce the mean turn, which would reduce the area. Increase the distance between windings as much as possible by using extra thicknesses of insulation. The use of interlayer insulation between each of the individual layers in a winding reduces intra-winding capacitance, as does using heavier enamel. Avoid bifiler windings. Redistribute the voltage and the charge by using multiple section bobbins. Progressive bank winding, or Z winding, which is where you wind across and then you jump back to the beginning and you wind across again and jump back and so on, versus the winding back and forth across the length, which is called C winding. And you can use a Faraday shield to drain away any charge, which is sometimes used between primary and secondary. As I reiterated before, techniques to reduce winding capacitance usually increase the leakage inductance. Core loss is one of the major losses we have in transformers. We looked at this last time with inductor core materials. Recall that core loss varies with frequency, with flex level, varies with temperature, and it even varies with your waveform and especially your duty cycle and the volt seconds you're applying. I showed curves like these where you can see many of the variations. It's important to note that core loss lines are not parallel to each other, so the slope does vary a little with the frequency. All these types of curves are generated from sine waves for consistency. The measurements are used to create coefficients for the Steinmetz equation, K, alpha, and beta. For ferrite, alpha, the frequency component, is around 1.6, and beta, the flex exponent, is between 2.5 and 3. This tells you higher flex density creates losses faster than high frequency. Most transformer designs are core loss limited, which means they do not operate at the maximum possible flex density because the core losses are too high. Switching power supplies typically use rectangular waveforms, so it's one of the things that we have to deal with. Square waves, that is 50% duty cycle, are easy because generally they have about 15% lower losses than the curves indicate. Just use them as they are, which gives built-in margin. Rectangular waves, those with on times less than 50%, get more inaccurate as the duty cycle decreases. There have been a lot of modifications to the original Steinmetz equation in the hopes of using sine wave parameters to estimate rectangular wave results. These have met with varying levels of success and adaptation. We covered a lot about cores in the inductor session, so here I only want to touch on a couple things about ferrite cores, which are the most widely used for switch mode power supplies. The concept of using metal oxides as a high-frequency material was first proposed by Hilpert in Germany in 1909, but he did not successfully make any useful material. The first successful ferrite was developed in Japan in 1930 by Kato and Taki, who went on to form the TTK Corporation. The first nickel, zinc, and magnesium zinc came from Schnook at Philips in the Netherlands in 1945. There have been a lot of improvements in ferrite materials, mostly by purifying the raw materials. It seems all possible combinations of materials have been tried, and they continue to work on it. The thing most people do not appreciate about ferrite is that the composition of the material only affects some of the properties, and other properties are affected by the processing. This means if you process the same composition two different ways, you'll have two different characteristics. These two charts illustrate the dilemma core material manufacturers face with regard to producing new compositions. These are topographical graphs that, in this case, show the initial permeability of the material based on the varying composition of three elements. The one on the left is nickel zinc, and the one on the right is sendust, powder material. In both cases, there's only a very narrow specific ratio that gives the peak permeability. Any slight deviation in permeability falls off by orders of magnitude. The result of this is coming to the point where one property is dominant, so you must choose. On the left chart, the vertical axis is iron oxide and the horizontal axis is magnesium oxide, and the resulting materials are grouped into two categories: low power loss or very high permeability. You can't have both. On the right are the four main areas of material optimization. Moving to one quadrant means giving up some of the other properties of the other quadrants. This is because only incremental improvements can be made in materials. However, all is not lost. In reality, you often only need one of them to be the best. An example would be a high-frequency transformer. In all likelihood, it'll be core loss limited, so a high BSAT is irrelevant. This chart shows performance factor. Performance factor is a product of frequency times flux density at a particular core loss level. In this case, 500 milliwatts per centimeter cubed at 100 C. Frequency is along the bottom, and it shows you that different material mixes have an optimal operating frequency. Where the lines peak is the optimal operating point for that material. Back in 1947, more than 70 years ago, Schnook postulated that due to geomagnetic resonance, there was a limit to the permeability and the operating frequency of ferrite. It translates to the higher the operating frequency of ferrite, the lower will be the permeability. This is known as Schnook's limit, and so far it's held up. You'll find that all high-frequency ferrites have low permeability. Winding losses are the other main loss in transformers. These are governed by the law of conservation of energy, which means at low frequency in DC, current flows where the resistance is the lowest. It also distributes uniformly within a conductor to minimize the I2R losses. At high frequencies, it tries to minimize the inductive energy. That's the energy transferring in and out of the magnetic field that comes from the current. And this usually results in higher I2R losses because the current does not distribute uniformly. This is the result of eddy currents created by skin effect and proximity effect. To review, skin effect is the phenomenon of current flowing on or near the surface of a conductor when there is high frequency alternating current. It generates a magnetic field, and by Faraday's law there will be induced currents, and by Lenz's law those currents will oppose the current that created them. These are called eddy currents. In the conductor you can see that on the inside they are facing the current that's creating them, therefore subtracting and resulting in a lower net current in the center. On the outside, they are flowing in the same direction, adding, resulting in higher current. This results in a distributed current density within the inductor. This finite element picture and the current density profile above it show high current density at and near the surface and low density in the center. This is why at microwave frequencies, conductors are tubes. Skin depth, as defined by this formula, where ρ is the resistivity of material and mu is the permeability of the material, is the depth at which the current density has fallen to 36.8% of the surface density. Because resistivity increases with temperature, we want to use the 100 C value in calculations. Skin depth for copper at 100 C in millimeters is simply 76 divided by the square root of the frequency. The key point to understand about skin effect is that it's defined for a conductor well away from the influence of any other magnetic fields. However, in transformers, we have wires and windings that are side by side. This is where proximity effect comes into play, where the current in one conductor is influencing the neighboring conductors. If we take two wires with current flowing in the same directions, the wires will attract because the magnetic fields at the interface are going in the opposite direction, canceling each other, and there's no force between them. When the currents are flowing in the opposite direction, the wires repel because the magnetic fields of the two wires add at the interface, creating an area of high field intensity. I should clarify that in order to make it easier to illustrate, in the conductors above and in the following slides, I'm using conductors whose thicknesses or diameters are much greater than skin depth. In a transformer, we have both situations. Within windings, the currents are flowing in the same direction. Between the windings, that is, between the primary and secondary windings, the currents are flowing in opposite directions. This finite element cross-section of windings illustrates the combined effect. What you see is one winding in the center, we'll call it the secondary, with 5 turns of large diameter wire, and on each side a split winding, we'll call the primary, with many turns of finer wire. The colors represent current density, with red being the highest. In the center winding, the side-by-side effect shows little current in the adjacent turns, and the current is concentrated on the facing surfaces. There's little benefit from the large copper area. The smaller primary wire shows less of the side-by-side effect, which indicates smaller wires are better. The proximity effect plays a far greater role in transformers. It's possible to calculate the effects of these eddy currents using Dowell's equations, which gives us a multiplier for the resistance so we can determine the winding losses. In a transformer, almost all the magnetic flux is in the core because of its high permeability. In the winding space, the permeability of the conductor, the insulation, and the spaces are practically the same. There is leakage flux and flux created by the winding currents. To simplify, I'm showing here a cross-section of a transformer with 3 foil turns for the primary on the left and 3 foil turns for the secondary on the right. The crosses and points indicate unit currents and the direction, in or out of the screen, with the number indicating the magnitude. If we trace the flux path, the blue line, around the winding, we have to conclude that most of the magnetic force is concentrated in the area between the windings. The field intensity between the turns is the product of the number of turns and the current divided by the winding length. From our last session on inductors, this is like the gap. As we trace paths through the core and around the increasing number of turns, we see that the field intensity builds as we move from the right to the left, until at the interface between the primary and secondary, the field intensity is the greatest. This is consistent with the previous slides. The primary current flows in the opposite direction, so the field intensity then decreases. At the same time that a unit of current on the right is going into the page, it's inducing a unit of current into the adjacent turn, going in the opposite direction. Because these two turns are joined together in series, you can only have one unit of current net, so you have to have a second unit that's induced in to counteract the first, to cancel it. But now I have 2 units, which will induce 2 more units of current on this side, plus the original current. You can see how this builds quickly. The result of all these actual circuit and induced currents is higher power loss within the winding. In the first layer you have the expected I squared R losses, but in the second layer you have the I squared R loss from the induced current on the right side of the foil plus the I squared R losses on the left, where there is twice the current squared. That means 4 times the power loss plus 1 equals 5 times total for just this layer. It gets worse with each layer. The third layer has both 2 squared and 3 squared for a total of 13 times the winding loss. This builds up very quickly because there are 2 exponents. The higher the frequency, the shallower the skin depth, which means the need for smaller conductors. By the way, the same thing happens in inductors. Now you know why we want the fewest number of winding layers in high-frequency transformers. Back a couple of slides, I showed how field intensity builds up with turns, current, and the number of layers. MMF diagrams are a way to show this in a graph. Here's a transformer with 3 layers of 4 turns for both the primary and the secondary. The force builds up until the current reverses. You'll see how we use these for calculating AC winding losses in a moment, but first I want to point out that the leakage inductance is stored energy, and the highest energy will be there where the greatest field intensity is, which is exactly between the primary and secondary winding. Sometimes shields are placed in this spot to either reduce the capacitance as a Faraday shield or for safety. Either way, this is the worst place because the strong magnetic field will induce eddy currents in the shield material, which is often copper foil, creating additional losses. Interleaving windings is one way to reduce the maximum MMF because it lowers the number of ampere turns per section. By splitting one winding, the MMF is cut in half, reducing the eddy currents and the leakage inductance. Thinking back to the finite element figure of winding currents I showed earlier, one interleave is the equivalent of doubling the winding length. More interleavings are not normally practical in power transformers because each primary to secondary interface requires extra insulation, quickly using up the available space. In order to apply Dowell's equations, we need to understand the concept of winding portions. A winding portion is a group of layers that contain one position of 0 MMF and one position of minimum or maximum MMF. For a 2-winding transformer, each winding would be a portion. For an interleaved one, as shown here, the inner and outer windings are a portion, and the center winding is divided into 2 portions because the MMF passes through 0. A portion is a group of layers that go from 0 to a maxima or a minima to 0 and back to 0, positive or negative. In 1966, in Europe, P.L. Dowell wrote a paper, Effects of Eddy Currents in Transformer Windings, where he applied the mathematical approach used to derive eddy currents in motor armatures to transformers, specifically signal transformers. At the time, switching power supplies were in their infancy. The first commercial 20 kilohertz switcher came out the following year, and it would be another 10 years before the first dedicated controller IC was built. To calculate the equivalent AC resistance, Dowell made simplifications to reduce the problem to one dimension. He made wise choices because we're still using the method nearly 60 years later. After determining portions, we need to reduce the windings to the equivalent foil layers. Starting with round wire, we convert it into square wire of the same cross-sectional area. The next step is to combine the squares into one equivalent foil. This reduces the winding length, so we need to stretch it, but by doing so with the same thickness, increases the area and reduces the resistance. To compensate, we calculate a porosity factor, F sub L, based on the number of turns in the layers times the wire height divided by the winding length. Finally, we can calculate phi, which is the ratio of the layer height times the square root of porosity over the skin depth. This is the equation which gives the ratio of AC resistance to DC resistance. You'll see this in a lot of literature in various similar forms. It's quite involved, but if you enter it into an Excel spreadsheet or MathCAD or MATLAB, Once you've done it, and from then on, you'll just enter a few parameters each time. This is what you get if you plot a series. The vertical axis, F sub r, which is the ratio of AC resistance over DC resistance. The horizontal axis is phi, which we calculated 2 slides previous. The lines represent different numbers of layers in the winding portion, including a few with half layers. The goal is to be under the red line, which means your AC resistance is only 1.5 times your DC resistance. You can see it doesn't take much to go above the line. On the right side, all the lines become linear and parallel because at this point the conductor is so much greater than the skin depth that it's just a constant ratio. If you normalize this chart by dividing FR by phi again, you get this chart, which clearly shows that for every number of layers there's a minimum FR, and you can never achieve an FR of 1 with more than one layer. If you look at the top layer line for 10 layers, the best you can do for an FR is just over 3, which means the AC resistance will be 3 times the DC resistance. You can also go too far to the left and make the wire size too small. Another way to look at it is presented by Snelling in his book Soft Ferrite. Here the red line is the same FR line equals 1.5 on the left, but the vertical axis is now phi, and the horizontal axis is now the number of layers. Using the formula in the upper right, you can calculate and plot a slope based on your winding length, porosity, turns, and skin depth to determine the optimal number of layers for that combination where they intersect the F sub r line. The forward converter is the first topology that uses a true transformer where energy is transferred instantly. It's an isolated form of buck regulator. The transformer with its own switch and rectifying diode supplies pulses to the buck regulator portion. This is very convenient when there needs to be a large change in voltage, say from 48 volts to 1 volt. A straight buck regulator would be using a 2% duty cycle, but with a transformer, the turns ratio can reduce the voltage and the duty cycle can be closer to 50%, ideal for both the transformer and the filter inductor. When we close the switch, the current flows through the primary, and at the same time the secondary diode D2 conducts. Power is transferred instantly and supplies the inductor, building up the magnetic field as in a buck converter. Diode D3 is blocking and the capacitor is supplying most of the load current. D1 in the reset circuit is blocking. When the switch opens, D3 conducts and the energy in the inductor can resupply the capacitor and the load. On the primary side, D1 also conducts, resetting the core through the reset winding. The forward converter uses a unipolar pulse, so it operates only in one quadrant. The on time drives the core up the BH curve and the reset drives it back down. Normally the turns of each winding are the same, therefore the T on must equal T off, limiting the duty cycle to 50% max. The reset winding only carries magnetizing current, so it's much smaller wire size, often wound bifilar with a primary. This shows in more detail the concept of reset and what you must watch out for. In these BH curves, the blue dashed line is an ungapped core, which is what you want to use for a transformer, and the orange is a gapped core that you'd use for an inductor. The remnant points are different. You have less flux range swing delta B with the ungapped and less energy storage. Remember, in a transformer you do not want energy storage. The on time drives the flux up and the reset drives it back. If it didn't, by only going one direction, the core would eventually go into saturation. Here you can see the benefit of Ferrite method using BH curves. It lets you see more easily where the remnant point is, which is not always given in the tables. The reset concept is that there must be an equal amount of applied volt seconds and reset volt seconds applied to reset the core. When the primary and reset winding have the same number of turns, the time and voltage are the same, and that limits the duty cycle to 50%. But you can go higher than 50% duty cycle if you increase the reset voltage by increasing the reset turns, or you can go the other way around. It's all a matter of equal areas shown in these waveforms. This principle of equal volt-seconds applies to all bipolar waveforms as well, which do it naturally, but if they're not equal, then the result is flux drift, which could also cause core saturation. If a second switch is added to the high side and a couple of diodes, you have a two-switch forward converter. With this arrangement, you can dispense with the reset winding. It's a very rugged circuit because it also divides up the source voltage, and the switch stress is limited. It operates by turning on both switches at the same time. D1 and D2 are reverse bias blocking. When the switches turn off, the polarity reverses and the diodes conduct, returning the magnetizing energy to the source and resetting the core and clamping the voltages to the supply rail. The price is extra components and a high side drive. Moving on, this is the push-pull circuit. It's the first circuit to make full use of the BH loop, going plus and minus on the curve. You can see it's like two forward converters back to back. You can always recognize it because the transformer will have a center tap so that both switches can be referenced to the low side. Only one switch operates at a time, alternatingly. When Q1 is on, D1 is conducting, and when Q2 is on, D2 is conducting. During the off periods, both diodes conduct as freewheeling diodes. Again, the entire secondary is a buck regulator. The drawback of this circuit from a transformer point of view is we're only using half of the windings at any one time. It's like building two transformers on one core because each primary has the full input voltage at the input and you're only using one at a time. Though it makes good use of the core, it's not the best use of the winding space. In all the topologies with bipolar waveforms, you'll find a 2 in the denominator of the flux formulas because the formulas are for B max. The 2 divides delta V, the full flux swing, in half. The half bridge is a great improvement because now we're using the full BH curve and we're making full use of the winding space. But you need two capacitors to divide the input voltage in half, and then you switch between the top half and the bottom half, fully reversing the voltage on the winding to make it bipolar for each half cycle. With only the half of the voltage on the primary side, the turns will be lower, but this is offset by the higher currents requiring larger wire. On the secondary side, you have the standard Llc filter with the diode bridge also acting as a freewheeling diode for the inductor. Overall, a good and popular topology. The full bridge is used for high power. It has 4 switches that alternate between S1 and S4 on together and S2 and S3 on together to apply and reverse the full input voltage on the primary. This helps reduce the currents. It makes full use of the BH curve and full use of the winding space, but controlling and driving the switches is more complicated. The LLC is interesting. It's usually implemented as a half-bridge circuit and usually follows a power factor correction stage, which pre-regulates the input voltage. This is because in an Llc converter, the duty cycle is fixed and you regulate by modulating, by changing the frequency around a resonant point. The switches operate at close to 50%, which is the best pulse width. The resonant circuit is formed by the leakage inductance and the resonant capacitors, which gives it a sinusoidal-like waveform, which helps reduce losses. From a transformer point of view, the interesting thing is the resonant inductor is the leakage inductance of the transformer. So you only have one magnetic device, even though the schematic shows 2. This makes the design a little bit more challenging because now you have to incorporate a significant amount of leakage inductance, which you normally try to avoid. But it makes good use of the core and the winding space. Because transformers are used for isolation, they usually have to meet some safety agency standards. The standards today for most electronic equipment is IEC 62368-1, which replaces the IEC 60950-1. It places requirements on the entire system being built for electrical safety, energy safety, mechanical safety, heat and fire hazards, chemical hazards, and radiation hazards. It's a new standard, a bit different from the old one in that it's based on what they call hazard-based engineering. This is where you identify a source of a hazard, classify it, identify the transfer mechanisms to the operator, and then how to safeguard against it. For electrical safety in transformers, this usually means some kind of minimum insulation thickness and/or layers of insulation plus some creepage and clearance distances. One of the key differences between IEC 62368-1 over the previous standard is that they're trying to go away from being prescriptive based to being more performance based. In the old standard, they told you exactly what to do. In the new standard, it does the same, but it leaves the option open for new technologies. It allows you to demonstrate performance and to adapt new technologies without rewriting a standard. This is an example of how creepage and clearance distances are defined in the standard. Creepage is distance along a surface, the red lines in these figures, and clearance is the distance through air, the green lines. Both must be maintained in all parts of a transformer, where often the most difficult point is where the wires from the windings come out to the pins or leads. The amount of creepage and clearance depends on the safety level that's required, working voltages, the environment known as pollution index, and the insulation material. Some insulation materials are more conductive than others, and this affects the distances allowed. In the bottom left figure, the arrow points to what would be tape. Tape has insulation value if you're going perpendicular through the surface, the thickness, but not along the surface. Margin tape in transformers is only used to provide mechanical distance. The many details for determining creepage and clearance are outlined in tables like this. This one is from IEC 61558-1. This is page 1 of 3, and there are 3 sections like this depending on what you're doing. It shows the many things that you have to be considered: the circuit topology, the type of insulation, measurements, what pollution degree your device will be used in. All these different working voltages require different creepage and clearance distances. There's also distance through insulation, there's solid insulation, and there's thin sheet insulation. All these have to be considered when you're designing a transformer after you've figured out a core, turns, and wire size. The net result is a larger transformer to accommodate all this insulation. If the previous wasn't enough and you need your transformer to be a UL recognized component, there's an extra step. You need to follow an approved insulation system for the appropriate temperature class. These systems comprise of a group of materials that UL has tested and verified that they work together for some temperature class. The point is to verify that the mix of different materials are compatible with each other and will not degrade one another at the rated temperature. One of the interesting things about these systems is that they are independent of the safety standards. The safety standards like IEC 62368-1 might require 3 layers of insulation tape, but if you adopted this particular insulation system shown here and you were using 3M number 56 tape, you'd have to have 5 layers of tape to meet the inter-winding insulation. The insulation system will dictate exactly what materials you're allowed to use together, but it might have greater requirements than the safety standards, which of course the safety standards say are only minimums. You must use whichever is greater. The other interesting thing about insulation systems is often you'll see, for example, a 130-degree Class B material like tape allowed in a 155-degree Class F system. This can be helpful in certain situations. In summary, transformers appear to be simple devices that are made from just some copper, insulation, and a core. But in reality, there's a lot going on under the hood that makes them work properly in any application. On top of the magnetics design, safety agencies add many additional requirements. It's often not appreciated how much the mechanical and manufacturability aspects play a crucial role in a successful design. We have many resources available to you, which include a wide selection of standard transformers for common applications, which you can easily access at we-online.com/redexpert. Nevertheless, for many reasons, the standard part may not fit your projects and you need a special. They are only a call away at Würth Electronics Midcom. This concludes my presentation today, and I'll be happy to take any questions that you might have. Okay, here's a question.
The question is, what about epsilon r of the core material concerning C/PF regarding high frequency power electronics? Wouldn't that be an important parameter for a data sheet in the future? I'm working with GAN, and the best solution is an in-house built transformer concerning our research studies, because there are very limited information about cores on that topic. Yes, when you get into the higher frequencies, you have to consider, especially if you're modeling using like finite element to model a core, not only do you have to have the permeability, but you have to model the permittivity of the core as well to get an accurate simulation of core losses. That permittivity, which we normally consider with a capacitor dielectric, does play a role. And what you find is that at high frequencies, there's a skin effect in the core itself. So especially on the large cores, you're going to have the same skin effect in the core with the flux, and it's not going to be uniform like it is at low frequencies. So that has to be included. I believe in the data books there is some general numbers for permittivity in the core data, but it's not listed with each material. Is usually just listed as a general for either nickel zinc or manganese zinc. So I hope that answers that question a bit. If not, ask it again. Next question is, what's the reason for bifilar windings are not used in power transformers? The simple answer to that is that the safety agencies don't the safety standards required you have creepage and clearance between the primary and the secondary. So you have to have some minimum distance or layers of insulation. So it would be theoretically possible to use something like triple insulated wire, which is magnet wire that has 3 layers of insulation on it, and you could bifilar wind, but then you'd really only be making a part that had 1-to-1 turns ratio. And the other thing is, I believe they've changed the standard a little bit now, so you actually have to have not just the triple insulated, but you have to mechanically separate the layers. So even though you use triple insulated wire, you can't wind like magnet wire right on top of it again. So in the end, it's we use most of the transformers to have a high turns ratio so we can optimize the duty cycle. So in that sense, bifilar windings don't make any, are not useful. The next question, are audible effects only present when FM is used in PMIC, or are the windings actually vibrating? Usually audible effects is the result of the core moving. So it's usually a core, if it's not solidly glued together and it has a chance to vibrate, then that's usually the source of audible noise, is the loose core. I mean, the windings, yes, at a very small level, the windings do move. I mean, if you scale up to a utility scale transformer, when there's current flowing through those windings, there are tremendous forces that are trying to either contract or repel. So you have those same forces even as you scale down, but of course at a much smaller level. So usually noise is as a result of a core that's not as secure as it should be. So I hope that answers that a little bit. The next question is it possible to use copper foil for power transformers, let's say in Llc topology, and still meet reinforced insulation? Oh, yes, copper foil is usually used for low turn count and high current. Secondaries is the typical application for copper foil. There are ways to meet the reinforced insulation by applying tape. It's usually wrapped around the foil, or the physical distances have to be, that's one way to, wrapping tape around the foil is one way to reduce the creepage, to have the creepage and clearance that you need without making the transformer bigger. But yes, copper foil is commonly used even usually just for low turns, maybe only up to like 5 turns or so, but the high current, low voltage secondaries is quite common for copper. The next question is, can you please describe the Z winding structure versus the C structure? Also, which one would you prefer for high power? So the C structure is normally when you wind a coil, you start at, say, the left side and you wind a bunch of turns to the right side, and then you just keep winding more turns back to the left, and then you go to the right, and you just go back and forth. That's called C winding. Z winding, what you do is you say you start at the left, you wind over to the right, you put one layer of turns, and then instead of winding the same turns back, you move the wire. You basically make one loop and you come back to the left side, and then you wind the individual turns on again from the left to the right, and then you bring that wire back to the left side and wind it. And the idea is that in C winding, when you wind back and forth, so you say you start at the left, you go to the right, you come back to the left, the voltage potential between those two layers is the highest there, whereas on the right side it's literally 0. So you have a high voltage difference between the two turns, the lower turn and the upper one. When you Z wind, you reduce that in half because you've only gone one layer, you come back to the beginning again, so you actually reduce the voltage difference between the two layers in half. And where you can reduce the voltage, you'll have less capacitance. So you do that when you need low capacitance, and it really doesn't matter what size the transformer it is.